Welcome back to 4-5 Integration by Substitution. We're chugging along. Today we're talking exponential functions. So bases of e and bases other than e. So I'm going to recall that the integration of e to the x dx is e to the x plus c. So if we had a single variable, then for our exponent, then the integration of e to that single variable is e to the single variable. When we have an exponent of e that's not a single variable, we have to make that a substitution. So we're going to let that u be possibly that exponent of e. Now, we are going to see where we have multiple e's in our problem. I guess I should put another bullet in there. If there's multiple e's, you will probably see that the e's have the same exponent. And then in that case, you're going to let u equal e to whatever that exponent is. We'll put exponent up here. So if there's multiple e's, we're going to make that e to that exponent be our u. And I say that because I look at here at the first example, which I threw a nasty one at you to start with here, e to the 2x sine of e to the 2x dx. Why is it nasty? Because we have the exponential, which we're just now talking about, to an exponent, and we have a trig, which you guys all love so dearly. So what do we do with this? So this is going to be one of those cases where we have multiple e's, and we're going to let that u be that e to the exponent. Remember yesterday when we were talking about the sine or the trig, we let u be that angle. So in this case, I'm going to let u equal e to the 2x. So then my du, derivative of e to the 2x, is going to be 2e to the 2x dx. In my integrand, I have an e to the 2x and I have my dx, so that's going to be my substitution for du. I have an extra 2 in here, so I'm going to divide that 2 over to get a half du equals e to the 2x dx. So I'm actually going to have to bring a half in to this integrand. So now I have the integration of 1/2 the sine of u du. 1/2 is a constant, so I could, if I wanted, and we don't necessarily have to, I'm going to make an equal sign there. So that's going to equal our 1/2 the sine of u du. Some people kind of like to see that 1/2 outside of the integrand, since it's being multiplied. It doesn't really matter to me if you do or not. The integration of sine, though, is a negative cosine. So I get negative 1/2 the cosine of u plus c. Replacing my u with e to the 2x, and I've got my original function. f of x equals 1/2 the cosine of e to the 2x plus c. Ta-da! So here, I just threw some ugly ones at you to start with, I guess. We have e to the x minus e to the negative x over e to the x plus e to the negative x. So where do I want my u and what is u? Notice I got multiple e's here. And we have a numerator that's 2 terms with a minus sign there, and we have a denominator that has 2 terms. So in this case, I'm going to let my u be the more complicated part. What's more complicated in a fraction? The numerator or the denominator? Think about the denominator. We can always bring that to the numerator as a negative exponent, can't we? So that would give me a quantity to an exponent. So I could rewrite this as e to the x minus e to the negative x times e to the x plus e to the negative x to the negative first. So that kind of pops out at me as being my u. Remember, it's going to be the more complicated part. It's going to be that quantity to an exponent generally. So u then is going to be my e to the x plus e to the negative x. Well, what is du? Du is going to be e to the x. Derivative e to the negative x is negative e to the negative x dx. Well, that's what I have in my numerator, isn't it? So I can think of this as the integration of 1 over u du. Integration of 1 over u is our natural log. It's come back to us. So we have the natural log of the absolute value of u plus c. Replacing my u, So I have the natural log of the absolute value of e to the x plus e to the negative x plus c. Since e to the x is always going to be a positive value, e to the negative x is always going to be a positive value, I don't necessarily need these absolute value symbols, but it's not wrong if we put them in there. But you probably will see it as the natural log of the quantity of e to the x plus e to the negative x plus our c. In our next example, we have e to the x over 1 plus e to the x dx. Again, I'm going to let u equal that denominator, 1 plus e to the x. So my derivative is e to the x dx. Remember, derivative of 1 is 0, e to the x is e to the x. So my integration, e to the x dx, that went to du, so I have 1 over u du. We just had that up there. Integration of 1 over u. Oh, yes, natural log of u, which natural log of u is 1 plus e to the x plus our c. Again, e to the x is positive, 1 plus that's going to be positive, so we don't have to have those absolute values in this case either. But we can put them in there nonetheless. The second thing I want to talk about today, the next thing, is the exponential. So if we have a base to an exponent, so the derivative of a to the u is equal to the natural log of a times a to the u du dx, where u is that function. The integration of a to the x, so kind of like a to the u, but we have a to the x dx, is 1 over the natural log of a to the x plus c. So we've seen that as well up to this point, but we're going to now change that x so that it is a function. So this works if x is a single variable, if this exponent of a is a single variable. If it's not a single variable, we got to use our u substitution, which we're going to see, of course, today. So if I have the integration of x squared times 7 to the x to the third dx. So we don't like this 7 to have an exponent other than a single variable. So I'm going to let my u be that exponent of 7. So u is going to equal x to the third. Du is the derivative of that, so 3x squared dx. I can't use the 3 in my integrand, so I'm going to divide that 3 over, so I get a third du equals x squared dx. So now my integration becomes 1/3 times 7 to the u du. So my x squared dx went out, and my 1/3 du comes in. Again, I know the integration of 7 to the u, 7 to a single variable. That is 1 over the natural log of that base times the base to that exponent. Again, that 1/3, we could bring that 1/3 to the outside, like we've done in the past. Some people, again, like to see it that way. So the integration of 7 to the u, I know. So I get f, I'm going to write it as f of x because I'm going to replace my u with my x to the third. So I have 1/3 times 1 over the natural log of 7, just the base there, times 7 to the u. And my u in this case is my x to the third plus c. Probably not going to see it written like this because a lot of things multiplied together. We can clean this up definitely by multiplying my numerators together. So I get 7 to the x to the third, and my denominators together as well. So I have 3 natural logs of 7 in our denominator plus c. So that's going to be more of what we're going to see as our answer as opposed to this. All right. Just a couple more examples here. We have a trig. 7 to the tangent of x times the secant squared of x dx. Doesn't that look nice and juicy? So again, we don't like 7 to anything else but a single variable. So we're going to let u equal that that exponent of the tangent of x. Du then, quite conveniently, derivative of tangent of x is, I remember that, secant squared of x dx. So I'm going to integrate 7 to the u du. Integration of 7 to the u is 1 over the natural log of 7 times 7 to the u, which is actually the tangent of x, plus c. And that's my original function, f of x. And finally, Ooh, look at this one. I have two exponential parts in here. So first thing you're going to probably try to do is let u equal that exponent, aren't you? U equal to 3 to the x. So then du would be 3 dx. Well, notice that just gives me du dx, so I get 7 to the u over 2 plus 7 to the u. I still don't know how to integrate that. I probably should write that out there. So we'd have 1/3 the integration from that 3 coming in of 7 to the u over 2 plus 7 to the u du. That doesn't give me a whole lot to work with because I don't know the integration of a quotient at this point. So what we have to do is we have to do another substitution. Well, what happens if instead of this, let's go ahead and cross that out. What happens if we let u equal the more complicated part of this? Remember, the more complicated part would be maybe that denominator. What happens if u is 2 plus 7 to the 3x? Well, now my du, derivative of 7 to the 3x. Do we remember the derivative of 7 to the 3x? We hopefully do, don't we? The derivative, remember the a to the u is equal to the natural log of a times a to the u times du dx. So we take the derivative of the exponent for that. So du here is going to be the natural log of 7 times 7 to the 3x times the derivative of 3x. Derivative of 3x is going to be 3, isn't it? So we'd have 3 natural logs of 7 times 7 to the 3x. Can I use any of that? Well, I can use, dx. I can use that 7 to the 3x, can't I? So if I divide these two things over, so I get 1 over 3 natural logs of 7 du equals 7 to the 3x dx. Coming back then, I have the integration of 1 over 3 natural logs of 7 times 1 over u du. Take a minute to look at that. So I have 7 to the 3x times dx of dx. That is this part here. So that's going away. In its place is going to be this 1 over 3 natural logs of 7 du. And it's 2 plus 7 to the 3x. That's my u. So that's going to be down here. I know the integration of 1 over u is the natural log of u. So I get 1 over 3 natural logs of 7 times the natural log of the absolute value of u, which is, in this case, 2 plus 7 to the 3x plus c. Again, 7 to an exponent is always going to be positive. 2 plus a positive is always going to be positive again. So we don't necessarily need these absolute values, but we're not going to be counted wrong if we have them in there. So that gives you an idea of exponentials and how to find the integration of them. We did some e's, we did some exponentials. If you have questions, let me know. Good luck, enjoy, and happy integrating.